Hello and welcome to the Respond webinar. Throughout the presentation, all participants will be in a listen-only mode. For those of you listening, please be aware that you can participate in the question and answer session by submitting questions at any time via the Q&A box on your screen. I'll now turn the call over to Paul Marshall. Please begin.
Thank you. Good afternoon and welcome to our third webinar on our low carbon network funded project, Respond. Respond is an innovative active fault management project. My name is Paul Marshall and I'm the Respond Project Manager. Thank you for registering to take part in our webinar today. Our audience is a broad mix of industry participants representing network operators, energy suppliers, equipment suppliers, energy industry participants and end consumers. Hopefully this webinar will have something of interest for all of you. A quick look at the agenda for today. First, I'm going to provide some background to the Respond project, particularly for those who have not seen Respond before. Then I'll give an overview of our progress to date, a review of the Respond techniques, where we're up to in the trials analysis phase, customer, and then the next steps. Then at the end of the presentation, there will be an opportunity to put your questions to me and other members of the Respond team. The format of the webinar includes a presentation which takes around 30 minutes, followed by a question and answer session of around 20 minutes. Please submit your questions online during the webinar using the box on screen, and myself and the project team will answer them at the end of the webinar. The Q&A panel at the end of the session will be myself, Paul Turner, the Innovation Manager, Steve Stott, our Technical Lead, Kieran Bailey, the Trials and Analysis Workstream Lead, and Tracy Kenley, who has been the Innovation Customer Delivery Lead. Respond overview. Respond is the first UK demonstration of an active fault management solution that avoids traditional network reinforcement. It is a £5.5 million project which was competitively won through Ofgem's low carbon funding. The project started in January 2015 and is supported by several project partners as shown on the slide. These help us to maximise the benefit from the project. Respond went live in May 2016 and we're in the second year of the trials analysis phase of the project. The trials analysis phase finishes in May 18 with the project closed down in October 18. A quick overview of the hypotheses that we intend to prove during the project are: Respond is faster and cheaper to apply than traditional reinforcement. It will deliver a buy order of fault level mitigation solutions based on a cost-benefit analysis. It will facilitate active fault management using retrofit technologies and commercial services. It will enable a market for the provision of a fault current limiting service. It will use existing assets with no detriment to their health. And it will reduce bills for customers by reducing network reinforcement costs. When fault level approaches arises above the fault level rating of network equipment, the fault level assessment tool, which is now embedded in our network management system, will enable or disable one of the three innovative techniques designed to manage fault current. The three techniques are adaptive protection, a fault current limiting service, and the IS limiter. All three techniques, when enabled, respond after a fault occurs, reducing fault current so that every item of network equipment operates safely. For the fault level assessment tool to operate correctly, we need an accurate and real-time network model. The network management electrical model is derived from existing data systems, including geospatial information systems. Any real-time changes to network configuration will be presented to the fault level assessment tool. The tool is designed to calculate fault level after topology change or periodically after 5 minutes, allowing near real-time modelling. We have had some ongoing issues with data quality for the fault level assessment tool. Therefore, at the end of the project, we need to take a view whether we're going to use it as business as usual. First technique I'd like to look at is adaptive protection, also known as sequential tripping. We have this installed at 7 sites across our network. Our network is already designed to break fault current and isolate the fault section of the network using circuit breakers and other protective devices. Adaptive protection changes the order that the circuit breakers operate to safely disconnect the fault from the rest of the network. Using redundancy built into the network, we can ensure that no other customers will go off supply as part of this change. This is a photograph of one of the adaptive relays that we've got a 7 installation, just to sort of give you a view of what adaptive relays look like. To provide some examples on how adaptive protection operates, this is how our network works at the moment. Electricity is generated by power stations around the country connecting to the national grid. From here it flows down to local distribution network owners, also known as DNOs, like Electricity North West. Electricity is then distributed to homes and business throughout a network of smaller substations, overhead lines and underground cables. Here you can see domestic and business customers on the right of the diagram, and a customer with a combined heat and power plant on the left. Adaptive protection alters the sequence our network breakers operate. The red squiggly line or the arrow depicts a fault in our network. All protected devices start to operate, but the one closest to the fault operates first and disconnects the customers on the network beyond the fault. In this example, the red circuit breaker would operate first, removing the fault from our network. However, in this example, the red circuit breaker fault level has been exceeded. So the fault level assessment tool could enable any of the circuit breakers in yellow so that they will open quicker than the red circuit breaker, reducing the fault level on the network so the red circuit breaker can operate safely beneath its fault rating. Next, the ICE limiter is our second technique, is a current limiting fuse. We have 2 sites with full installations. We have 5 sites with IS sensing units. Our standard equipment will normally identify a fault and respond to it within a couple of hundreds of milliseconds. This may seem fast, but the fault current will have already peaked within this time frame. An IS limiter will operate within 5 milliseconds before the fault current reaches its peak. When enabled by the fault level assessment tool, the IS limiter will monitor the normal current flowing through it. When a fault occurs, the IS limiter detects a rapid rise in current and responds by setting off a small explosive charge which breaks the normal flow of current, removes some of the fault current flowing through our at-risk piece of equipment and allows it to operate safely. IS limiters are in use on private networks in the UK and public networks worldwide. However, they're not used on UK public networks. As well as proving the effectiveness of this technology, Respond will review the safety case and the use of these devices on UK networks. As part of the project, we have effectively replaced an existing circuit breaker with an IS limiter at 2 locations on our network. The first site is at Bamber Bridge in Preston. At this site we have a substation busbar section open. The IS limiter is acting as a closed busbar section breaker. If the fault level is exceeded for any of the circuit breakers at the substation, the fault level assessment tool will enable the IS limiter. If a fault then occurs, the IS limiter will operate at 5 milliseconds and effectively open the busbar section at the substation, which halves the fault level any of the circuit breakers will see, therefore operating safely. The second site is at Broadheath in Manchester, where we're using the IS limiter in a different configuration. At this site we have the IS limiter acting as a closed transformer breaker. The green line and blue arrow at the right of the slide are just a bypass switch used during the trial and would not normally be installed. If the fault level is exceeded for any of the circuit breakers at the substation, the fault level assessment tool will enable the IS limiter. As before, if a fault then occurs, the IS limiter will operate in 5 milliseconds and effectively open the transformer breaker at the substation, which reduces the fault level any of the circuit breakers will see, therefore operating safely. These are external photographs of the ice limiter. The one on the left is at Bamber Bridge, and the one on the right is at Broadheath in Manchester. Broadheath has 2 containers during the trial. The second container is to house the bypass circuit breakers. The photo on the left is the ice limiter, which is made up of 2 parts. The first on the far left is a circuit breaker controlling the ice limiter, which provides a 3-phase trip when any of the ice limiter fuses blow. Attached to that is the ice limiter, which has horizontal withdrawable fuses on a carriage. The photo on the right is the bypass switchgear at Broadheath. The third technique is the fault current limiting service, which enables us to disconnect the fault current generated by industrial, commercial and generation customers using new technology which we trialled under Respond. This commercial solution will enable customers to earn rewards and will benefit all distribution customers through reduced reinforcement costs. We believe there is significant equipment out there that is contributing to fault current that could be part of the solution. Our challenge is to identify customers who have such equipment, engage with these customers to explain, respond, and see if and how they can contribute. As an example, electricity flows through the 2 transformers to the factory on the left and the homes and businesses on the right. At the factory, different types of equipment are connected to the network, including a large motor and a large generator. A fault occurs, the red squiggly line again, the fault current rushes towards the point of the fault. All protected devices start to operate, but the closest one to the fault operates first and disconnects the customers on the network beyond the fault. If we can reduce the fault current to a lower, safe level before the circuit breaker operates, we won't need to upgrade any of the network equipment, which can be very expensive, or the customer may not have to pay as much for a new connection. One way of reducing the current is to disconnect the customer's motor or generator. This would happen instantaneously, using new technology deployed as part of Respond. Once the faulty section has been isolated, the motor or generator can be switched back on. The rest of the customer's equipment would remain on during this fault, as only the selected items of plant will be interrupted, and only until we have disconnected the fault, which could take up to 10 minutes. In this example above, the red circuit breaker's fault level has been exceeded. So the fault level assessment tool could enable any of the circuit breakers in yellow at the customer's premises, so they will open quicker than the red circuit breaker, reducing the fault level in the network so the red circuit breaker can operate safely beneath its fault rating. As I mentioned earlier, we are now 16 months into a 2-year trials analysis period. And so far, highlighted in blue, we have had 9 successful activations of the techniques. 2 of which is at yellow, have been the operations of the ice limiters at Bamber Bridge, which has split the high voltage bus bar and reduced the fault level. In green, we have had 7 adaptive protection operations, 3 at Atherton Town Centre, 1 at Blackpool, 2 at Littleborough, and 1 very recently at Earlham. We have had no failures of any of the techniques. I'd just like to step through a number of the waveforms we have received from a number of the faults. The first one was Atherton Town Centre in July 2016. So we have a red, yellow, blue waveform and the neutrals on the bottom, and it's a sort of timeline as the activations progressed. So as you can see here, we have normal current and fault current. In this instance, we have a phase to earth fault. The yellow phase is made up of the load and the fault current. At this stage, it develops into phase to earth fault. We still have reduced earth current, but it's still present. The adaptive protection, the relay, sees the fault and operates, in this example, in 35.5 milliseconds. The adaptive protection circuit breaker operated in 100.3 milliseconds. As a result of that, we do have the fault level magnitude has been reduced. I must point out at this stage, we don't have any fault levels on our network at the moment, so therefore if we did have a fault level, the magnitude would be a lot greater. Later as a fault develops, it moves into a three-phase fault, and then 800 milliseconds later the feeder circuit breaker opens, removing the fault at reduced fault level magnitude. On the 28th of August again at Atherton Town Centre we had another activation. As before, we have a mixture of fault current and normal current. At this stage we have a phase to earth fault, which develops later into a three-phase fault. The adaptive perfection sees the fault and operates in 23 milliseconds. And the adaptive protection circuit breaker operated in 93.6 milliseconds. Again, we had a fault level magnitude reduction. Unfortunately, the recording was outside of 1,000 milliseconds, so we didn't actually record that. But the feeder circuit breaker did operate, removing the fault again at reduced fault level magnitude. Again, Atherton Town Centre has been busy there. We've had on the 19th of September another activation. Again, we have a mixture of normal and fault current. At the early onset, we have a phase to earth fault. The other phase up is made of your load and your fault current, which develops into a phase to earth fault. Again, we have earth current present. The adaptive protection again sees a fault and operates in 35 milliseconds. And the adaptive protection circuit breaker operates in 100 milliseconds. And again, we have a fault level magnitude reduction. Later, as a fault develops, it goes into a three-phase fault. And then the feeder circuit breaker again opens in 800 milliseconds, reducing the fault level. The next fault we did actually have was adaptive protection again on the 3rd of April at Black Bull. Unfortunately, we do not have a waveform present, but the incident started as a face-to-face fault on Lansdowne Hill 6.6 kV feeder. The adaptive protection stage 1 operated, which tripped the 6.6 kV bus section. The Lansdowne Hill South Feeder Protection Relay detected the fault, but did not operate as the fault was cleared by a midpoint circuit breaker further down the network. Because of mismatches between the disturbance record and the adaptive protection relay, unfortunately we were unable to recover a waveform for this event, but it was concluded that the adaptive protection did operate correctly. We've had another fault on the 8th of May at Littleborough Primary. As before, mixture of fault and normal current. The adaptive protection sees a fault and operates in 18.5 milliseconds, which then triggers the adaptive relay circuit breaker, which operated in 99.7 milliseconds. Again, we had a fault level magnitude reduction, and then a normal feeder circuit breaker operates in 1.5 milliseconds, removing the fault at reduced fault level magnitude. So that is the adaptive protections we've analysed. We had an ice limiter fault on the 22nd May at Bamber Bridge. Unfortunately, the ice limiter did operate very, very quickly in milliseconds, so we couldn't actually recover any waveforms. But the investigation has proved the red phase ice limiter responded to a fault, operated and interrupted the fault. The time interval between the Bamber Bridge local feeder and the earth fault alarm was in the region of 10 milliseconds. The series circuit breaker opened in 51 milliseconds after the tripling of the ice limiter. And the event log indicated the Bamber Bridge local 11 kV protection operated in 1.37 milliseconds, so it did operate correctly. Just to give you some visual examples, the photo on the left is the withdrawable carriage of the ice limiter, which shows the three IS fuses and inserts. The IS limiter is a combination of an extremely fast-acting switch, which can conduct a high current but has a low switching capacity, and a fuse which has a high breaking capacity mounted in parallel. In order to achieve the desired short opening time, a small explosive charge is used in a storage energy mechanism to interrupt the switch, which is shown on the right picture where the green dot shows a trip indicator. When the main conductor has opened, the current still flows through the parallel fuse, where within half a millisecond the current is limited and finally interrupted, which is shown by the striker pin operated in the red phase on the left picture. We have had a second fault at Bamber Bridge on the 18th of August, which is still actually under analysis by our project partners WSP. The fault on the left again shows the withdrawable carriage of the IS limiter, which shows this time the yellow phase striker pin has been activated. The fuses have been recovered and been sent back to Germany for refurbishment, and it's only the fuses that have been activated require replacement or refurbishment. The fault current limit service enables us to disconnect the fault current generated by industrial, commercial and generation customers using new technology which is being trialled under the Respond project. Significant time and effort has been spent developing an engaged customer panel to test and develop customer engagement material, customer surveys and contracts, which initially appeared to prove there was a market for the fault current limit service. However, in reality, our aspirations was to achieve 750 surveys and interviews, and unfortunately we were only able to achieve 103 surveys. And of these surveys, only 47 expressed an interest within our region, and of these, only 13 were willing to engage in any discussions. We're still actively working with United Utilities to identify sites, and also negotiating with one external customer to participate in the trial. But in this particular case, the winter triad market is making the fault current limit service uncompetitive. The fault current limit service proposal has been much harder to implement than first envisaged. Why, you may ask? The main reasons customers are not willing to participate in the trial are shown on the slide. For most customers, it was essential for them to have power 24/7. A 10-minute constraint would have a significant impact on them, especially industrial customers. However, there was some interest from new connections, but they were not connecting within the project timescales, plus the techniques haven't been proven yet. Customers were also worried about how often they go off supply and what impact that would have on their equipment. Also the impact on their daily operations, their reputations and their ability to export power, and the loss of revenue, but more importantly was any existing export or triad contracts they had in place were not competitive with what we were offering. Customers were also not keen to relinquish control of their equipment. Many employed third parties to operate electrical equipment, which could mean their equipment being off supply longer than our 10-minute constraint. The financial incentive is a key driver of the target market, but only if it offsets all risks and has to be more attractive than the existing commercial agreements to be competitive. So what are the lessons learned from our customer engagement? The distribution network operators, the DNOs, community must develop greater commercial understanding of their target market. The challenges of transitioning customers from an expression of interest to active participation in the service. The loss of critical plant, even for short duration, can have a significant impact on a business. Assessment of risk versus the incentives and savings available will be fundamental in an organisation's decision-making process when considering any elective commercial service. Potential conflicts with other commercial arrangements and industrial players in the commercial service market have been identified as a significant barrier to participation in the trial. This highlights that great commercial acumen is required by the DNO community to better understand the acceptability of this type of scheme amongst customers that are already well positioned to offer other lucrative commercial services to third parties in an expanding and competitive marketplace. The next step from today is to continue to monitor techniques for the remaining 9 months to see how the techniques work. We will be reviewing and examining the key questions of the project with the aim to answer them. We'll still continue for ongoing customer recruitment for the fault recruitment service. We will be building the safety and reliability cases for each of the techniques to be deployed across the UK DNOs. We'll be producing a biodata and cost benefits to the various fault level mitigation techniques. The presentation is now complete. I would like to introduce my colleagues who have been working the project to answer your questions.
Okay, thank you. Thanks for that, Paul. First question then that we've been asked, and I think this question is asking how does the fault level assessment tool determine which of the fault level techniques should be initiated? And the answer to that one is actually it doesn't. Each technique is independent on its own site. So the fault assessment tool will just turn on the technique at that site. It doesn't select which technique. So we're trying all the techniques independently. Next question then is, how is the safety case progressing?
Yeah, well, we just, WSP, our partners, are undertaking the study for us. At this moment in time, we've just had the first workshop, which is just looking at the adaptive protection method. Following that, we'll do the IS limiter and also look at the fault current limiting service. There will be synergies across these, so what we learn off the adaptive protection will be better for the other two cases. So far, as I say, we've just done the workshop, pending now we're going to engage with the HSE, other DNOs, etc. to hopefully put our robust case forward to the HSE. So it's very early days at this moment.
The next question is, how do you approach customers to take part in the trial?
Right, Paul, I think that's one for me. It's been very frustrating. It's actually been quite challenging, as Paul alluded to earlier, to engage customers. And there are obvious reasons for that. The customers that we are looking to engage are very large industrial and commercial customers, both demand and generation. A lot of those customers are very well placed to have contracts, demand-side contracts, capacity contracts with the transmission system operator, and those are very lucrative, and they are keen not to put those arrangements at risk. We have essentially approached all operators of synchronous generators and motors within the Northwest. So we've looked at our generation database, we've looked at all high voltage connected customers in our region, we've gone outside region to get customers to take part. We've been speaking to trusted partners who have got a more direct relationship with industrial and commercial customers, specifically the ADE and energy. And we've just used all public domain databases that we have been able to access to get information from customers, initially to take part in the trial, to understand the price point and commercial acumen of this particular concept. And as Paul mentioned earlier, once it did become, it was implied that there was a commercial appetite for this type of concept at that phase, actually translating that to get customers to participate in the trial has been extremely difficult. So we are working with our project partners, United Utilities, at the moment, and we think we've secured 2 sites, and we're still working with other external bodies to try and push this trial through, so at least customers going forward have the comforts that the technologies, the enabling technologies, have been trialled and tested.
Is the bypass circuit breaker required for BAU operation?
Okay, Paul, yeah. No, the bypass circuit breaker is not there for BAU operation. It was purely there because this is a trial. Obviously, very few people are familiar with the equipment, so the idea was that rather than waiting for somebody who would be specially authorised
to change the fuses. Our control centre can very quickly close the bypass circuit breaker and make sure we kept our current level of system resilience, so going forward we wouldn't be using a bypass breaker.
Why do customers need to wait 10 minutes before turning back on?
What we needed to do under a fault condition, we would go around to reconfigure the network through an automatic restoration system, then remote control switching. So we needed to make sure that the fault level or the fault on the network was removed before the customer contributing the fault towards would come back on supply. So that was why the 10-minute constraint was there. So for us to be able to reconfigure the network to reduce the fault level, so the customer could come back on.
This actually is one of the barriers that we have been coming across in our conversations with customers, because whilst there might just be a 10-minute constraint on our part, it's becoming very apparent that actually that resource isn't on site for customers to be able to actually reclose their own circuit breaker. So what might potentially be just a 10-minute constraint for us could actually turn out to be a very significant interruption of customers' equipment, which obviously has a very costly impact.
You mentioned data quality issues in the fault level assessment tool. Can you give me more detail on what these issues were? Yes, so the issues in terms of the tool were that to carry out the fault level assessment, we're using fields of data that haven't really been used before. There's a large amount of data cleansing required. So that data has been cleansed, and the fault assessment tool does work, but it's an ongoing thing really to keep the data up to date so it functions correctly. That's why we're looking at the viability of using the assessment tool post trial. Do you feel that the fault current limited service is a viable option post-trial?
We do potentially, but it's become very apparent that it is not a solution that is going to be acceptable to existing customers. What we feel, where we feel that this might sit, is for new generation customers particularly, as a new form of constrained connection agreement. Now, there are still a number of issues that will need to be overcome concerning how we control the customer circuit breaker, and there's quite a lot of associated safety and security issues around that are clearly going to come out in the safety case. But potentially by offering a new constrained connection at the fault level, which would essentially be an extension of the G59 regs, DNOs could secure a fault level response from new generation customers, and critically without the need for ongoing customer payments to those customers. So once the customers have confidence that the technologies have been proven, we feel that this type of agreement would allow our new generation customers to connect onto networks that are approaching fault level much more quickly and particularly more cheaper than by traditional reinforcement. And that gives customers the opportunity to make a connection in their desired location, where otherwise costs and timescales would be prohibitive. So we recognise that constrained connection agreement does seem to provide a viable possible commercial solution, but I think it's really important that we need to be mindful that this technique, even in those circumstances, is only going to be suitable to a relatively small number of customers.
Why did the solution not operate for all of the substation trips?
Yeah, I can take that. Basically, a number of the faults out in the network were single-phase faults, and of a magnitude which was below the threshold of the adaptive protection settings, such that it wasn't required to operate. So in the settings for the adaptive protection, have got to be above the potential earth fault current, and therefore, because it didn't operate, and following investigation of each of the primary trips, we found that they were earth faults, and therefore correctly did not operate.
What's the plan for implementing the technique on the network after the trial?
I think that the plan, the first stage is to develop the safety case, have 3 robust safety cases, to have them peer reviewed, to make sure that they're suitable to be employed. Then we will produce a buy order of each techniques and where it's cost effective to employ them. I personally, as project manager, been contacted by a number of different people, particularly on new connections, looking to use IS limiters and also adaptive protections. So definitely is a market out there, but we need to prove the techniques are safe, what the cost benefit is for each of the techniques and where it can be employed, and use it as a toolbox to use each different techniques at each different connection point.
It's worth just pointing out that the buy list will include all techniques, on some of the other DNO's projects, including WPD.
Flexity grid project as well.
Would this approach be viable for intermittent peaking generators?
Okay, I'm not 100% sure, but I'll take the question, Paul. When it says intermittent, basically, I presume this is implying with generators coming on and off the network. Having a fault level assessment tool there, as these generators come on, assuming we have the visibility of these via the SCADA system to show that they're connected, the fault level tool would carry out the assessment, and if it felt that the break fault rating, I must stress that we are only looking at the break fault rating, not the make or the peak make, then the adaptive protection, if the generator is part of, if we've actually put the particular technique either at the generator custom site or when we put it on the primary site, if that's where the fault level issue is, it will actually enable the relevant technique. So it can work for intermittent generation as long as we've got visibility such that it can be taken into the SCADA system to allow a fault level calculation to be calculated based on basically a change of a circuit breaker.
That's all the current questions we have.
Right, thank you all very much for your time, and I hope there's been some views. And goodbye. Bye. Bye.
This now concludes our presentation. Thank you all for attending, and please ensure you fill in the survey before disconnecting from the webinar.